Concurrency is not parallelism. This was made famous by Rob Pike, one of the original designers of Golang. So what is concurrency? Concurrency is when you have multiple tasks that need to complete, but they do not overlap in time. As you can see, each of these tasks don't overlap before another one stops and resumes. Now, what is parallelism? Parallelism is when multiple tasks can run at the exact same time and their times do overlap. So as tasks start and stop, they can overlap the other ones. Each of these lines might represent a system thread in the OS that you're running in. Threads are execution units for a CPU to run instructions. So when you have a process, and process is mapping to a CPU, within that process you could have a single-threaded process or a multi-threaded process. Whenever a thread is run on the CPU, it starts executing those instructions when it needs to switch to a different thread. It's called a context switch. This is where the OS is managing the thread and it needs to save the current stack and the pointers and everything that needs to happen for when the CPU runs. And normally the maximum number of threads for a process is on the order of thousands to tens of thousands. You wouldn't see very much more than that because of the overhead that it costs. Now on Goroutines are also called coroutines in other languages, and these are managed by Go, and they're very lightweight execution. They only take about 4 kilobytes of memory, and they map to a system thread when they're executing concurrently. So as in our previous slide that showed the tasks that are running concurrently, they don't overlap. And so the Go runtime will actually determine which task needs to run at what time. So rather than your operating system such as Mac or Linux or Windows, within the Goroutine will pick which task needs to run, and it will actually save where it left off and resume from that point. And so the benefit of having Goroutines is that you can have hundreds of thousands of these. It has very, very little overhead. One of the main benefits of Goroutines is it allows the developer to write code in a synchronous manner while still getting the benefits of running code asynchronously, not having to write code using callbacks or await syntax. All this is handled by the Go runtime. You can also run Goroutines across multiple threads and CPU units. So if you set a setting within your Go program to run on multiple processors, this can also be handled, and it's managed by the Go runtime. Okay, let's put it all together. We have 3 threads here, thread 1, 2, and 3, and then we have these Goroutines here, which are in the different color boxes. So let's say Goroutine 1 starts up, and then at T1 it launches 2 more Goroutines. So you can see that these Goroutines are not overlapping. Goroutine 2 starts and finishes, and then Goroutine 3 also starts and finishes. Another example could be that Goroutine started and then it waited for a web request to come back, and so 2 could be paused and 3 could be started and then finished, and the request could come back, 2 could start again, and then 2 would finish. This is an example of one grouping of Goroutines all operating on the same thread. So there's lots of different options for this first section here. In the next section, at T2, let's say the Goroutine 1 starts up, and there's actually 2 new threads that start, thread 2 and thread 3. At the end of at T3, let's say Goroutine 1 spawns 3 new Goroutines, and you can see this at 4, 5, and 6. And 5 and 6 are actually working in parallel on thread 2 and 3. let's say your computer has more cores than just one core, and it's going to run those in parallel. So 4 will finish, for example, right here. Let's say 5 finishes here and 6 finishes there. So you can see that they all finish at a different time. So this is an example of fanning out work. We want to work on multiple items at the same time, and when they're done, we want to wait in Goroutine 1 for them to all finish. And that's what T4 is. We have Goroutine 1 waking back up again, and it's going to process the results that came from those Goroutines. And let's say Goroutine 1 ends and the program exits. This is the Go playground, and we're going to write some code. You can get to this at go.dev/play, and this is a very basic example of a Go program just printing hello world. Now what we're going to do is we're going to write a Goroutine, and what a Goroutine is simply Go followed by a function in order to run. So we're going to say go func, and then that is the function that will run. So we can actually create a function called hello. So over here, we're just going to write hello. Now let's see what that does. So as you can see, our print line didn't actually print anything. And this is expected behavior from Go because when the main function exits, all the Goroutines that we're running also exit. So if you think about it this way, when main is run, main is actually a Goroutine itself. And so when it runs from the top down, it will actually spawn off other Goroutines, and then once it gets to the end of the function, that's when the runtime will say, do I have any other functions that need to be scheduled? Well, the main function, when it exits, so it doesn't actually call the hello function because it is done operating. That is why this function is not written. This might actually be a question in some more advanced interview. What happens when the main function exits, and that's all the Goroutines end. Now what if we added a simple wait here? Let's call import time. And this is a little difficult for me because I don't have my IntelliSense here. So time.sleep, we're going to sleep 1 second. So it did actually print the hello. So why did this work? The time.sleep actually delays the execution of the Goroutine and allows the hello Goroutine to operate, and then once the sleep ends, then the main Goroutine ends as well. And so this is plenty of time for the printline task to complete. And so the program just exits at that point. Now I'm switching over to Visual Studio Code because our examples are getting a little bit more complicated and it's easier to see with IntelliSense, and I'm able to run programs at the bottom. So here's an example for Goroutine 1, just building upon what we used in the Go Playground. I'm calling Go Hello with each different name. Then I'm sleeping, and then for the function itself is actually printing the name. And so I already compiled this, and you can see that running the Goroutine will actually print out a different name in a different order every time. So you can't depend upon each of these Goroutines working in the same order. It's undefined in the Go runtime which will get run first, so you cannot depend upon that. Example of writing a Goroutine, you can actually write go func, and the function is actually just defined here, and then we call the function as part of the Goroutine there. And then within here, we're actually calling print number. And so you can see that I actually have a issue right here. It says loop variable I captured by func literal. So what that actually means is we are capturing I after it reaches the end of the loop. What you'll actually see is that the print number is printed mostly at tens because it ran through the whole loop before it was able to print. So in order to fix this, what we'll do is we will put a variable here, let's call it n, and then we're going to put I as the argument into this function literal, and then under this print number we'll put n, and save that and rerun it. So now we can see that there is no duplicate numbers and they're running in order. Now, one addition we could make to this, instead of using time.sleep, it would be much better if there was a way for us to just wait until all the Goroutines are done. And there is a very good way to do that. It's called a wait group. So we are going to create a wait group, and we're going to say WG is sync wait group here. It's declared but not used. So a wait group is a way for us to add Goroutines to the wait group, and at the end we will wait for it to be done. Inside the go function, we're going to add one because we are adding one Goroutine. So we don't want to put it within the go function because we don't know whether this loop will just finish right away and it will never be added, so then it would end right away. So what we want to do is at the top of the function within the Goroutine, we're going to do a defer call to wait group done. So what this will do is it'll put it at the end of the stack and run the done, so you can have as many commands right here as you need. Then down here, instead of the time.sleep, we do a wait group wait. Let's compile this, and it should run and exit really quickly. There it goes. So this is a much cleaner way of waiting for all the Goroutines to end, and rather than using a sleep, which is unpredictable, whether it will finish the program in enough time or not. Example, Goroutine number 3. In this example, we're going to use a slice of numbers, and what we're going to do is add 10, go through a loop of 10, and rather than printing, we're going to append the numbers together within the Goroutine. So what this is going to do is it's going to run multiple Goroutines, and they're all going to be trying to add to the numbers. So let's see what happens. You can see that I ran this multiple times, and this one only added 4. This one added multiple values, and then it went back to adding just 0, just 2. So it's a very unpredictable behavior here. And so if you're coming from a different language, such as Java or Python, C++, any other program language, generally what you do is you would have to write a way to protect this variable, and that's where a mutex comes in. And add a mutex here. I'm just going to call it mut for short. And then right in here, we're going to lock it and then unlock it after. So let's see what happens now. So now you can see that all the variables are added and there's no overriding variables. Here we have a similar example to the numbers slice is where I'm using a map string to an int, and this is done without protecting the numbers map. So let's see what happens down here. I ran it one time and everything worked correctly. Let's run it again a few times to see what will happen. Okay, so it looks like our program just panicked, and so if we scroll up, we can see what actually happened. Fatal error concurrent map writes. So this happens when we're modifying the underlying map from multiple Goroutines. So we definitely need to protect our map from concurrent writes, and adding the mutex is one way to do that, and we'll explore other ways to do that as well.